Hi, everyone. Thank you all for coming. I'm Karin Wolok. I lead our developer community at StarTree.
I am a committer and PMC on the Apache Pinot project. Currently, I'm a founding engineer at StarTree.
And we're going to be talking to you about optimizing the speed and scale of user-facing analytics using Kafka, Apache Kafka, and Apache Pinot. So I'll kick it off. I'm just going to give kind of some fundamental intro-level stuff. So first, we're going to talk about the different types of analytics use cases. So I'm going to go over 3 basic higher-level intro types of analytics use cases. So the first one is probably the most commonly known one. It's dashboards and BI tools. This is mostly used for internal purposes, and it's usually analyzed by BI analysts internally. This is probably the most popular, well-known use case for analytics. The next one is machine learning. So these are analytics use cases where the data is then ingested and processed into a system in some way or another. So things like fraud detection or anything that's kind of automated, this would fall into this category. And then the third one, which is my favorite, is user-facing analytics. So these are analytics that when you are building applications, you are providing your end users or customers of the applications, you're providing them with real-time analytics. So I'll dig in a little bit more into some of these use cases to make it a little bit more clear. So why should I care? And in this example, we're going to dig a little bit further into user-facing analytics use cases. So over time, real-time analytics has shifted. So it started off more of an internal use case, as we've kind of mentioned before, with BI analysts and dashboards and things like that, which is still very commonly used and highly valuable. But as time progressed, a lot of organizations started empowering their end users and consumers by offering them their own access to real-time analytics. And a lot of organizations have actually productized this capability. So they've actually created products that the value is to give their end users real-time analytics. And that's why you should care, because companies are literally productizing this entire category. So just to go into some examples of use cases, LinkedIn has a lot of cases of this, so this is why I like this use case a lot. So, a lot of people, I'm guessing most of you guys have used LinkedIn in some form, shape, or another. So LinkedIn has a thing, who viewed my profile, which is very commonly known. I think it's one of the most commonly used user-facing analytics use cases at LinkedIn. But basically, you have the ability as a user to see your own analytics of who viewed your profile. And then you have the ability to slice and dice this data by company or location and things like that, right? And this is a premium feature. You got to pay money for it. So that's one example. Another example of a user-facing analytics at LinkedIn is the newsfeed. Every time a user clicks on the homepage, they are basically querying this fresh data and getting relevant information on their newsfeed, things that were posted maybe seconds ago, and things that they have not seen before because we don't want them to get redundant information, right? So this is a similar process in terms of querying the database in real time. And then there's the talent insights. This is, again, another example of productizing your user-facing analytics, where you're creating applications and actually monetizing and productizing what you're providing the end user with real-time analytics and real-time insights. Another example of real-time analytics is the Uber Eats use case. So Uber Eats, they have the restaurant manager. They basically give over 500,000 restaurant owners the ability to access their own analytics to see the health of what's going on inside of their restaurant. And then it has things in here like missed orders, inaccurate orders, feedback, top selling items, things like that. And this is important to be in real time, right? because if something is going wrong, you need to know like right away, not tomorrow. So this is an example of like when the real time is really, really important. And okay, so another thing I kind of want to run, there's no slide for this, but I want to make sure that it's something that you guys do take away. I'm going to go back a slide just because I'm going to make sure you guys are paying attention and not reading the slides. So there's also another thing that organizations are doing when they're offering their end users real-time analytics, which is kind of important to take away, and that's actionable insights. Now, what actionable insights are there when you're offering your end users the ability to take action when they see something happening, right? So like with the Uber use case, for example, like if they see something happening, they should be able to act on that thing, right? And that's when you're empowering your user. And same thing with like the LinkedIn examples, with like the news feed. People can like things, they can share, and like the who viewed my profile. So it also increases your like engagement with your consumers. So we kind of went over like the different kinds of use cases, but as there's been a shift from internal analytics moving to external, like basically offering your end users real-time analytics, there's also been a shift in what you actually need to build these systems. And it comes down to like the latency has to be in milliseconds. Obviously, people are not going to wait a second. We know that. People are very impatient. Waiting a second is too long. And like the data freshness has to be also in seconds. And then also the concurrency, right? So this is one of like the larger challenges of like creating user facing real-time analytics, is that you have to be able to support a lot of queries concurrently at the exact same time with like a lot of dimensionality, which makes it quite complex when you're trying to build these kinds of systems. So what does it take to build a real-time user-facing analytics system? So there's a few things that you kind of need. It has to be able to ingest the data very, very quickly in real time, or as like near to real time as possible. It has to be queryable also in real time, or like as real time as possible, right? Milliseconds of time latency. And it also has to be scalable. So you have to be able to query this data set like on a very like very high throughput, right? So we know for one part of the system, I think one of the like there's like popular technologies like streaming systems, like Apache Kafka is a really popular one. So we know that like this can kind of handle one part of our system, but then we have another part that we have to fill in. So just going over the analytics landscape a little bit, you might already be using a data warehouse, and you'd be like, well, why can't I use a data warehouse? And the issue is with a data warehouse is the latency can often be very slow when you're querying the latency, and also the ingestion latency can also be kind of slow. And when you need everything in millisecond time, the solution that we're kind of looking for is in that corner, that OLAP solution. Yes. So some of the other types of solutions that I think people are trying to address this problem with, on one side, you have things that are like very, very high latency, but they have a lot of flexibility. And then you have in the middle, you have like your search-based systems, which are they kind of fall in the middle in terms of latency and flexibility. And then you have the pre-computing types of systems. And these are usually very, very low in latency, but the flexibility is also very, very low. So that's not really the most efficient solution. So introducing Apache Pinot. So Apache Pinot is a real-time OLAP distributed data store. Basically what it does is it ingests data from a variety of sources, including batch and streaming, and has the ability to kind of bring them all together, do some pre-aggregation, a lot of special, amazing, powerful indexes, and then make it queryable with very high throughput and very, very low latency. In terms of the maturity of the product, it's already been widely adopted. There are a lot of companies using it, and our community is like growing very, very quickly, which is really exciting. There's a lot of really interesting use cases in there too. And in terms of power of like the technology and its querying capability, I think some of like the largest Pinot instances are like 1 million ingested events per second, with 250,000 plus queries per second, still maintaining millisecond latency. So it's very, very powerful. And now I will hand it over to Neha.
So thanks, Karin, for telling us about user-facing analytics, user-facing real-time analytics, walking us through the challenges of exactly why it is so challenging to build a user-facing real-time analytics system in terms of like really low latency, milliseconds latency requirements, and extremely high throughput in hundreds of thousands of queries per second while ingesting the freshest of data, and then also introducing Apache Pinot as a system to solve this problem. So the rest of the talk, we are going to do a very deep dive into exactly what Apache Pinot is and why it is able to solve such high throughput, low latency workloads. Before we get into that, just like a high level overview of Apache Pinot's architecture so that we set some context for the rest of the talk. So data in Pinot is stored in the form of segments, and segments are like a portion of the data that is packed in a columnar fashion with indexes and metadata of that data. These segments are stored onto, so the first Pinot component I'd like to introduce is the Pinot servers. So these segments are stored onto the Pinot servers. So these servers host the data and also serve queries of the data that they host. Then we have the Pinot brokers. So these are the components that accept queries from the clients. They scatter them to the servers, get the results back, which they merge and then send back to the clients. And then we have the Pinot controller, which will kind of manage all the components of the cluster with the help of Helix for state management and Zookeeper as a persistent metadata store. So now we're going to get into the speed aspect of Apache Pinot and try to understand exactly what makes Apache Pinot so fast, starting with the ingestion. So let's say that in this cluster, we are trying to ingest from a real-time stream. Let's take the example of Kafka. Pinot also does support ingestion from other streaming sources like Kinesis, Pulsar, PubSub. So in this case, let's try to take a deep dive into how exactly the ingestion works with one such streaming system. Let's say your Kafka has a topic that you want to ingest from that has 4 partitions. Now, in order to start ingesting from this topic, you would create a table in the Pinot cluster. And once you do that, the Pinot controller will create a mapping from partition to server. And then based on this mapping, Helix will send state transitions to the Pinot servers to start consuming from the partitions that have been assigned to them. So as you can see, server 1 is now ingesting from the pink and yellow partition. Server 2 has been assigned to ingest from the green one, and server 3 is ingesting from the blue one. So on these servers, as they are ingesting the data is getting indexed in real time. This indexed data is stored in memory, and because of that, it's available instantly to start serving queries. So you can't keep this data in memory forever, right? So you have to periodically flush this data onto disk. So let's look at what's happening to the pink partition. Periodically, the Pinot server will take all that in-memory data, build a Pinot segment out of it, flush it to the disk, and also put it on a segment store, like we can use S3 or GCS for permanent storage, backup, and recovery. And then for that ping partition, a new consuming segment will be created to resume consumption from where we left off here. And the same thing keeps happening repeatedly again and again for that partition and also for all the other partitions independent of each other. And in all these actions, the Pinot controller is like the single coordinator that is coordinating all this. And because of this design, it is very easy for Pinot to react to changes in the cluster. For example, if there were capacity changes, if you had increase or decrease in the number of servers, or if a node goes down, or if there are changes to the number of partitions in your stream, or you change the replication settings of your data set. So all that happens is the Pinot controller will update that mapping, and then based on that mapping, Helix will make sure that it gets reflected in the state of the system. Now, if you don't have your data in a stream, but instead have it sitting somewhere in like a data lake, Pinot also has ways to natively just keep pulling data from the data lake in a continuous incremental fashion. So that's kind of the other way to get data ingested into Pinot. And now we're going to focus on the query aspect. So what makes Apache Pinot queries so fast? So bringing back the relevant components of the architecture from the diagram we saw before, we have the brokers, the Pinot servers, and then the Pinot segments. So when the query reaches the broker has to find the set of servers that it should fan out the query to. Once the query reaches the server, it has to find the segments that it needs to process. And then within each segment, Pinot has to figure out which are the exact records, which are the exact documents that it needs to scan in order to get the results and then compute the aggregations. Then the results are merged by the server across all the segments that it processed. And then finally at the broker, again, results are merged from all the servers that it processed. So at every point of this journey of the query, there are optimizations that we can apply to just reduce the amount of work done and make the query faster. Starting with the broker. So there are pruning strategies that we can apply to reduce the number of servers that the broker needs to fan out to. For example, we have some smart segment assignment strategies or some partitioning strategies. So to give you an example, let's say in this cluster you had a Kafka topic with 3 partitions, and then you could have configured Pinot to say that every server will get only 1 partition. So when you get a query that has, say, a filter predicate on the same column that was used to partition the stream, you will instantly be able to prune out 2 servers and only go to the 1 server that has that data. So similarly, once the query reaches the server, there are pruning strategies you can apply to reduce the number of segments that the server has to process. Some of the strategies here are just looking at the metadata inside each segment. We keep like the min value, max value for each column. So if you have a filter predicate, you could use that value and then just check whether you even need to process a segment or not. An even better way of doing pruning at the server level is to use bloom filters. So you could add some bloom filters and be even more accurate about what you need to prune or not. And then once you know which segments you need to process, there are filter optimizations you can apply to reduce the number of records that you need to scan. And these are mainly all the indexing strategies in Apache Pinot. And then finally, once you have the number of the exact records that you need to process, we have some aggregation optimizations that can help you compute the results in the fastest possible way. So we're going to talk a lot more about the filter optimizations or the indexing strategies. And some little context to start that discussion. Here's a little info about how the segment is structured in Pinot. So let's say you have raw data of this form where you have country, browser as columns. So inside a segment, as I mentioned earlier, data is stored in a columnar fashion. So each column is stored separately, and at the minimum, we keep like a dictionary and a forward index for each column. So if you look at this data, you have the data in a columnar fashion. So actually, you wouldn't have stored US, Canada, Japan. You would have just stored the dictionary IDs here. But now without any indexing, if you get a query like this, where you have a filter predicate on country, you would pretty much have to scan the whole column and then figure out exactly which records have the value you're interested in. So on top of this, we can keep building a lot of interesting indexes to reduce the number of documents that you have to scan to get your answer. So for instance, you could build an inverted index. So in this case, for every unique value, we would keep a mapping from value to a bitmap that will give you the exact matching document IDs instantly. So now if you get the same query, all you have to do is find US in that dictionary, and then you will go check your mapping, get the bitmap, and exactly know that immediately in a single lookup that you have to look at document IDs 1 and 4. You could also build a sorted index. So in this case, the column in question has to be sorted. And in that case, if it is sorted, you could simply store a mapping from the value to the start and end document ID. So again, this is going to be a very fast lookup compared to doing a full scan. Similarly, we have a whole bunch of other interesting indexes that are, as you get more specialized and more specific about your use cases, that you can start applying these. For instance, we have a range index, which is very useful for range predicates, so something like timestamp greater than or milliseconds epoch in between these two values. So this is very useful in like user-facing dashboards, because you often have to give them a view of a specific time frame, or in real-time anomaly detection, because you have to do kind of week-over-week comparisons. Then we have a JSON index. So with JSON index, you can, if you have nested, complex, arbitrary JSON strings, you could pretty much just ingest them as is, no need to do some pre-processing to extract your fields out. And then Pinot has the ability to, using this index, index every field inside your arbitrary JSON, and then you will be able to query it really fast. You don't have to sit doing all the JSON parsing and matching during query time. Another one is the text index. So this is very useful for free text searches using queries that have like or regexp. These two indexes are very useful for doing, say, log analytics or just reading semi-structured, unstructured data. We have geospatial indexes. So if you have data that you're storing in the form of coordinates, you can use this index to run fast geospatial queries on it. To give you an example, Karin talked about Uber Eats. So in that, she talked about the restaurant manager. But now we also have user-facing analytics in Uber Eats for the end users like us who are ordering food. So there's a feature called Orders Near You. So this is being powered today by Apache Pinot and geospatial queries. So you are being able to see that within a certain mile radius, what are the orders happening near you in real time? And that uses the geospatial index. Then we have some aggregation optimizations to just compute aggregations faster. We have theta sketches and hyperlog. And then we have a very special index called StarTree index, which serves as a filter optimization and also as an aggregation optimization. And then let's talk more about the StarTree index, and this is also why our company is actually named StarTree. It's inspired by this index. So StarTree lets you maintain pre-aggregations of certain dimensions, and it lets you choose exactly which dimensions you want to pre-aggregate. And it also lets you choose exactly which aggregation functions you want to store, and also how many values you want to pre-aggregate. So to give you an example, let's say you have data that has columns country, browser, device, OS, clicks, and you decided that you only want to do pre-aggregations for country and browser combinations. So then this is how your StarTree index would look. You would have like the root node or the star node, and then under that, you would have pre-aggregations on the first level for each country. Under each country, you would have pre-aggregations for browser. And then because we've configured that we only want to do pre-aggregations for these 2 columns, the StarTree index would stop here. And now if you get a query like this, where you have a filter predicate on country and browser, this is going to be just a single point lookup. It's going to be very fast because it's just a quick 2-step traverse and get the answer from the StarTree. And to achieve this, you didn't have to do pre-aggregation of everything, nor did you have to do anything on the fly. So in that way, StarTree lets you achieve a balance. It lets you pick your overhead between how much you want to pre-aggregate, which is bad for space, and then how much you want to do computation on the fly, which is bad for latency. So with StarTree index, it's very easy to quickly do fast drill down, roll up, and just point lookup queries are super fast. So this was just a quick walkthrough of some of the optimization techniques in Apache Pinot. Like we walked through the ingestion, through the filtering techniques, we walked through StarTree. And because of all these, Pinot is really able to shine when it comes to workloads that need milliseconds latencies, hundreds of thousands of queries per second. And so Pinot is kind of the perfect fit to be used with another streaming system when it comes to building user-facing real-time analytics. And then the shift from internal analytics to user-facing or external analytics is just one of the many trends that is happening in the real-time analytics landscape. So there's several other trends that are happening, and OLAP systems are being expected to adapt with them and evolve with them. For example, we have the shift from structured data to semi-structured data. We have the shift from approximate data query consistencies to strong, strict data query consistency requirements. We have a shift from just analytical style slice and dice queries to expecting that your OLAP data store will do full SQL semantics. We also have data explosion, so the shift from not just using your OLAP data store for hot data, but also wanting to just store all possible data into your OLAP data system, and also be able to do it in a cost-efficient manner. So I'm going to walk through each of these and then see what Pinot is doing to adapt to these trends, starting with semi-structured data support. So typically in an OLAP system, if you wanted to ingest semi-structured data, you would have to add a pre-processing layer in between to convert your semi-structured data to structured data. But in Pinot, we have added support for doing a lot of these common pre-processing operations natively. So we have, during ingestion, we can natively do filtering, flattening, add derived columns, or even do sorting, partitioning. And then you can also just simply not do any of these and store your semi-structured data as is, and then use the JSON index or the text index or geospatial indexes to just get your data fast and still reap the benefits of indexing. Next is the strong data and query consistency requirements. So typically, OLAP systems are append only and immutable. So you cannot do use cases that need, let's say, you have one primary key and then you keep getting incremental updates to that same primary key. To give you an example, if you have a trips data set and you get an event when a trip was taken and completed, and then later you get another event for the same trip ID, which is kind of adding a tip or adding a toll to the fare. So another example is, like, say you have an orders data set, and then you keep getting events for the same order ID as the status of that order keeps changing. So if you are treating all of these updates as inserts, then your counting is not going to be very accurate, and you also cannot present one unified view for that particular primary key. So in Pinot, we have this feature called upserts, which lets you insert if it doesn't exist, or update if it already exists. And this is really a very unique and game-changing feature for OLAP systems. So with this, we are very excited to see what new possibilities that use cases will unlock. So this feature was driven in the Pinot community by Uber. So those examples that I gave about trips and the fare being added later is like a real use case which motivated adding this feature in Pinot. The next one is the full SQL semantics. So typically, OLAP data stores only need to do analytical style queries, which are like filter, group by, aggregations, order by. And then if you wanted full SQL support, the recommendation would be that you add like a query federation layer. So even in Pinot, we used to say that if you want full SQL support or need to do complex operations like joins, you can add like a Trino connector on top of it. But now the Pinot community is headed towards full SQL semantics. We already have joins as an alpha feature released in Pinot. And we are also expanding that to add nested queries, window functions, and so on. A little bit more about what we are changing to be able to do full SQL semantics. So earlier when we saw the query execution diagram, we saw that it was a single stage scatter gather between the broker and the servers. And that's fine when you want to do just basic analytical queries like filter and aggregations. But if you want to do joins, then you might have more operations that you need to do after the initial filtering, such as do a local join or do some data shuffling. And if you rely on just one stage to do all of this, that's going to become the bottleneck. So we have added support for multi-stage query execution, which lets us now add all of these interesting complex query operations. The last one was data explosion. So typically, OLAP data systems tend to be tightly coupled. So they will use SSD or disk on local storage or EBS volumes. So if you keep on adding a lot more data, your storage is going to become very expensive. And then what data teams did to tackle this is use the OLAP data system only to store hot data and use some other system like Presto or something to store all the cold data. But then again, you have two systems, you have to do query federation, and people really just did want to start putting all of their data into the same system. So Pinot is adding support for tiered storage, with which you can configure a portion of the data to be locally and decide exactly which data gets offloaded to cloud storage. So with that, you get the best of both worlds. You can keep all your data in the same system and query it like it's in the same table. And that brings us to the end of the talk. So just a quick refresher, we talked about how Pinot is the perfect system for doing ultra-low latency, high throughput queries, and how it can provide freshness ingestion SLAs, how it is setting up some new trends with features like upserts, and also adapting to evolving trends like semi-structured data support or full SQL semantics and tiered storage. And that brings us to the end of the talk. Thank you so much. We hope this talk inspires you to go adopt user-facing analytics into your data products.
Thank you.